ISDE is an organization that analyzes and designs electronics that are going to be used in high reliability applications, especially those where they might be exposed to radiation. The main example of that is electronics that would be used in spacecraft, because once they get outside the Earth's atmosphere, they're no longer protected from all of the high energy particles that are flying around out there. So we design and simulate electronics to understand what the effect of those particles is going to be on the operation of the electronics.
We operate much like a small business. We have a fairly unique arrangement that involves academic research, industrial partnership, and entrepreneurship. We have the largest group anywhere that works in this particular area of application, radiation effects on electronics. So we've got people that span the range of activities from atomic scale physics up through system design.
One of the programs I've been working on is Rad Hard by Design, where we use design techniques to harden circuits for radiation environments. We want to provide designers with tools that allow them to easily prove their devices and designs before going to fabrication, which results in a cost savings to the programs and more confidence in the design before it gets fabricated. We've seen a lot of success out of this program. We've developed some models that have allowed designers to really understand what their designs will look like ahead of time, and we've seen a lot of first pass success in circuits that have gone on to prove themselves to be radiation hardened.
The goal of the CubeSat program is to verify predictions that are being made here on the ground. So we use accelerator facilities to characterize parts and predict on-orbit response. And the CubeSat platform allows us to put those parts into space and actually test those predictions.
Status check.
It's tense moments just before liftoff.
Go L55.
Early morning at Vandenberg Air Force Base in California.
T-minus 10.
Vanderbilt's payload, a tiny metal cube measuring radiation effects on electronics, is on board, one of 13 miniature CubeSats in this mission. The Vanderbilt payload was sponsored by NASA. The small payloads were loaded into a large nose cone, then lifted to the top of the rocket.
3, 2, we have RD-180 ignition.
The Atlas V rocket takes the CubeSats into space. Vanderbilt worked with AMSAT for this flight. The team has done billions of calculations regarding radiation effects on electronics.
I'm working on how electronic components behave in the presence of radiation, like the radiation you would find in space.
RD-180 is running normal.
Their goal is to develop electronic systems that can better handle the harsh conditions in space.
Looking good.
At a predetermined location in space, the CubeSat is deployed and begins its separate mission.
So it'll be mounted like right where my hand is.
Back on Earth in a Vanderbilt classroom, researchers begin their work, following the satellite in orbit and analyzing data it sends back to them from outer space. For Viewcast, I'm Barb Kramer.
We do a lot of testing, both of things that we design and things that are provided to us by some of our collaborators. And a lot of the testing is done here on campus. It's a very fast and efficient way for us to characterize new technologies. One of the most interesting things that we're doing is to understand the response of emerging technologies, and that ranges from two-dimensional materials to new memory technologies. I think the key advantage that we have is that we have such a broad range of expertise that we can bring to bear on these problems.
It's very important for research to be applied because that's where the rubber hits the road. That's where the research actually impacts systems and our sponsors and their needs.